All right, we are back for segment 3 of section 6.2. Last time we had basically only dealt with equations that could be factored, which tend to make them quite a bit easier. But now I think I want to show you a couple of solutions where I think maybe the ones I have are not really as hard as I thought they were. I think maybe we'll have some better ones at some point, but I can actually just make one up, and we can kind of struggle through it together, because I think I can show you in about 2 different applications kind of the sorts of problems that you'll see. They tend to be kind of long, so let me just kick over here a second, and we can get on to it. All right. So section 6.2, we're now on page 7. All right. So here's an example of a problem that we may or may not be able to solve with. Well, I don't think this one can be factored, but let's see. Let's just see where we're at. I'm just kind of looking at it. I don't usually prepare too much just given problems. So let's say we have the equation 2 sine squared of x plus 3 sine of x plus 1 equal to 0. Now, I'm not guaranteeing, but I think that possibly could be factored. The way to tell, and when by factored, I mean factored with whole numbers for coefficients, which makes it kind of a little more approachable. So the way that you can check that, I don't know if anybody remembers this, but in algebra, you talked about, okay, so there's this thing called the discriminant, and it's really like the square root business in the quadratic formula. But it allows you to just kind of look at stuff fairly quickly and say, okay, this number squared is 9, and if I'm going to subtract 4 times 2 times 1, which is 8, from it, is that a perfect square? If it's a perfect square, then this thing is factorable with integer coefficients, right? So I know that this can be factored. And so I'm going to propose that maybe the factorization is 2 sine squared of x plus or minus something. Probably got to be plus because both of these are plus. And then sine squared, or sorry, these are not squared, I'm sorry, sine of x plus something, don't know what it is yet. So what I need is, and this one's actually pretty trivial, because what I need is for the cross, the outside plus the outside plus the inside, when you FOIL this out, needs to add up to 3 sine of x. And it turns out that that's pretty simple. It's just 1 and 1. So there's our complete factorization of this quadratic equation. And now this gives us 2 separate branches of the solution. So I'm not going to do all the algebra, because I think it's, I mean, you've seen it enough times that there's not a whole lot of need to do that. But from this equation, you're going to get that sine of x is equal to negative 1/2. And from this equation, you're going to get that sine of x is equal to negative 1. Okay, so sine of x equal to negative 1/2, you're going to get, and since we've done it so many times, I'm just going to kind of allude to it. X equal to, well, the inverse sine of negative 1/2 is negative pi over 6, which I think we've done that one already. And then don't forget 2 pi times n. The alternate root for this one is actually, and I think we've done that as well, is negative 7 pi over 6 plus 2 pi times n. For this one, the solution, you're not going to end up with, and this sometimes happens with these quadrant angles, you're not going to end up with 2 branches here. There's just the principal root and its coterminal angles. And I'll leave that to you to kind of look through that, puzzle through, and realize why that is. But you'll have x equal to negative pi over 2 plus 2 pi times n. So if we give ourselves the same restrictions that we only want the solutions between 0 and 2 pi, then x would have to be a member of the set that contains, let's see, 11 pi over 6. This actually, I'm sorry, I've got a mistake here. This should actually be plus 7 pi over 6. So 7 pi over 6. And then this one, that's out of the range. So when I add 2 pi, I actually end up with 3 halves pi, 3 pi over 2. So there's 3 solutions to this equation. All right, so this one is not very exciting, but let's try one that maybe is a little more exciting because it involves a calculator. I don't know. We didn't really talk about some of these other methods, like if you've got rational expressions and things of that nature. So maybe let's try one like that. Well, let me just get what I've got, and then we'll try to dream up one where we have to use the quadratic formula. So suppose you have this equation: 2 cotangent squared of theta over cotangent of theta plus 3 equal to 1. Now this, and let's say that theta between 0 and 360. So that's the clue that it's a degree version now. So first off, with quadratic, we didn't really talk about how to deal with rational expressions and rational equations, but if you remember from some intermediate algebra, what you simply do is you clear the fractions first thing. So you have to factor all the denominators, find the least common denominator, multiply everything by that, and then boom, you end up with something that's no longer has any fractions in it at all. But you won't see ones that are very, very complicated in the text. They could get complicated, but we just don't really. The book is not written at that level. So the simplest thing to do here is to just clear the fractions by multiplying everything by this factor downstairs. And so what you end up with is an equation: 2 cotangent squared of theta equal to cotangent of theta plus 3. Now this is a quadratic equation in cotangent, and we need to kind of bring to bear the quadratic techniques that we know. So we need sort of in descending order equal to 0. So I'll move these over to here, change the sign. We've got 2 cotangent squared of theta minus cotangent of theta minus 3 equals 0. And again, I think this is going to be one that is factorable. I'd almost guarantee it. And I'm thinking, the reason that we know that's true is because this is going to be 1, well, maybe not. Gosh. I think our determinant, our discriminant has to be, let's see, so we got 1 squared plus 12? Let's give it a shot. I think that it's going to be factorable. So how about 2 cotangent of theta, and we don't know if it's plus or minus, and cotangent of theta, plus or minus something. So this is the old guess and check method. So what I want is I want these to, the product of these two things to be -3, and I think I get what I'm after if I have if I use -3 here and +1 there. Let's just check that. Let's FOIL that out real quick. You've got 2 cosine square cotangent squared theta, and then -3 plus 2, we have minus cotangent of theta, and then -3 times 1 is -3. So this is the proper factorization. And what this leads to is 2 possible solutions. One is where, and let me do the easy one first, this one here. and then I'll shift to another sheet of paper. So cotangent of theta plus 1 equal to 0 implies that cotangent of theta equal to -1. So theta will be equal to the inverse cotangent of -1 plus pi times n, or sorry, not pi, 180 degrees times n, because now we're working in degrees. And the inverse cotangent of -1, well, we have to know where cotangent achieves -1 in quadrant 2, right? Because that's the range on inverse cotangent. So this becomes 135 degrees plus 180 degrees times n. And if you're doing it in this particular range, the two solutions, which we'll collect them here at the end, but they come out as 135 degrees and also 315. Okay, so let me move to the next sheet. This is where it gets a little bit interesting. So I'll kind of keep this here just so you can see what the other factor is. But page 8. Okay, so here you had the second factor. So we're trying to solve that factor equal to 0. So we've got 2 cotangent of theta minus 3 equal to 0. We want to solve this equation. So simplifying that, isolating the quote variable, isolating the trig function, we get cotangent of theta equal to positive 3/2. Now, there is no angle like that we know about that necessarily it's not one of these known values of cotangent, right? So what we're left with is that we should just simply use a calculator to do this, because the process is no different. It's that theta will be equal to the inverse cotangent of 3/2 plus 180 degrees times n. And I don't know what this is. But if I use a calculator, I find out that it happens to be 33, and I'm just going to do this to one decimal place, 33.7 degrees plus 180 degrees times n. So, which would give you the two solutions, 33.7 and also, what's that, 213. Okay, so combining both these results, I have that theta is a member of the set containing the angles 135 degrees, 315 degrees, 33.7 degrees, and 213.7 degrees. Now, the only thing that I kind of didn't mention when we started this problem that has to do with, that's peculiar to rational equations, is that you can't have that, you might, as you're doing these problems, and I don't think it, like I said, the book is not particularly tricky with these kinds of problems, but it's possible that one of those factors would have given you a result that cotangent of theta equal to -3. And that would have created a problem, because you can't have this denominator equal to 0. Even if it was if all the algebra gave you a solution. That's something that comes up when you're dealing with rational expressions well, I think the first place you see those is maybe even like beginning algebra a little bit, but I don't think you get to equations there. But by the time you're in intermediate algebra, you see that, and it's kind of, you're reminded of it. It's like, hey, you got to check to make sure it actually works in the equation. But this one doesn't suffer from those problems, so I didn't really make a big deal about it. Okay, so let me just try to cook one up that will require a because I don't really have one handy, but I think I can probably make one that has a solution. And hopefully it's a solution that isn't too ridiculous. So let me do one, let's say 4 sine squared of x minus, let's say minus 2. I want to keep these numbers kind of high. Minus 2 sine of x minus 1. I'm pretty sure that that one will have 2 real solutions. And I don't think that, let me just do some quick math here. So the discriminant would be 4 plus 8. Now 4 plus 16, so 20. So yeah, this one's going to have some bizarre values, bizarre solutions. They'll have square roots and stuff in them, which is what I was looking for. So if you try for a minute, you know, and you should really, if you see an equation like this, this is a quadratic equation in disguise. And if you see this, you really should spend, you know, 30, 40, 50 seconds, maybe even a minute, trying to figure out if that thing can actually be factored. And if it can, go ahead and factor it, because that's a much easier way to handle these problems. But there is a test, and they taught you the test in college algebra, and that's what I was doing there for a minute. I was just kind of going through the test, making sure this will end up being something weird that I want. Once you convince yourself that this will not factor, you can use the quadratic formula. And so instead of using x, we're looking at sine of x. So sine of x is equal to negative b, or 2, plus or minus the square root of negative 2 squared minus 4 times a, which is 4, times c, which is negative 1, all over 2 times a, which is 4. Okay, so now we just need to do a little bit of simplification to this kind of ugly looking fraction over here. So it's, let's see, the first step, we've got 2 plus or minus, well, we've got 4 plus 16, that's the square root of 20 over 8. And we can make that a little bit simpler because this has a factor of 4 in it, which will pop out and make that a 2. So we have 2 plus or minus 2 square root of 5 over 8. And now everything top and bottom has a factor of 2 in it, so we can make this as simple as possible. We've got 1 plus or minus square root of 5 over 4. And this is pretty exciting to me because one of these is a known value. I mean, this is like, I think it's going to come out at like 18 degrees or something, which is going to be slick. If you remember when we talked about a long time ago, we talked about the third triangle that produces results, and one of the solutions came down to something that looked an awful lot like that. So, all right. So what do we do with this? Now that we have sine of x equal to that, you have to ask yourself, are both solutions in the range of sine of x? And it turns out they are, and that's because of this large denominator, right? You're going to get basically, this is a little, when you take the square root of 5, it's a little bit larger than 2, right? It's just a little bit larger than 2. And so if you add 1 plus a number a little bit larger than 2 and divide it by 4, that's going to be a number less than 1. And if you take 1 minus a number a little bit larger than 2 divided by 4, you're still going to get something that's, it's negative, but it'll be greater than negative 1. So it's in the right range, and we'll actually get two separate equations out of this that we each need to solve. So let me jump to another page and show you how this is going to function. So this is probably our last problem. It's going to put me a little bit over on the time that I want, but I also think this is the last segment for this chapter. So I think this is page number 9. And recall, what we're trying to do is solve these two equations. So sine of x equal to 1 plus root 5 over 4. Okay. I mean, it's an uglier looking number, but we have done this problem exactly, right? This is in the range of sine, so x will be equal to the inverse sine of 1 plus square root of 5 over 4 plus 2 pi times n. Or x will be equal to pi minus the inverse sine of 1 plus root 5 over 4 plus 2 pi times n. Now these are both going to end up with solutions that are numeric. So I'm going to pull out my calculator. I'm not sure you can quite see it, but I'm going to take 1 plus square root of 5, I'm sorry, 1 plus square root of 5, and then divide that by 4. And now I take the inverse sine of this number. Look at that. Oh, that's an angle. This would be so much slicker if this was in, it was in degrees. Maybe I will, maybe, you know, just for illustration purposes, so I don't get so messed up with the radians, because that's actually an exact radian value too, but this is not normally how these things work out. It's just, it was a fluke of the equation that I pulled out. So let me just kind of modify this and say, instead of doing these with pi's, how about we do this with 360, and then this becomes 180 minus plus 360 times n. Okay, so I just did a quick flip so that we're not working in radians. So here's this solution which we just showed. The inverse sine of that number is actually 54 degrees, which is really cool. So x equal to 54 degrees plus any coterminal angle, or it is equal to, well, 180 minus 54 is going to be 126 plus 360 degrees times n. So that's what we get from the first branch. I think we're going to get something else that's awfully cool on the other branch as well. But notice that the only difference is really this plus or minus. So I can basically use all the work that I've got there and just repeat it. So for the other branch, we have x is equal to the inverse sine of 1 minus root 5 over 4 plus 360 degrees times n, or x is equal to 180 degrees minus the inverse sine of 1 minus root 5 over 4 plus 360 degrees times n. And let's do the same thing we did before. I think it's going to come out to like 18 degrees or something, because that's something I do actually kind of recognize, that ratio. But let's verify. So first we have 1 minus square root of 5 equal, divide by 4. Oh, it's going to be negative, so it might be negative 18. And then let's take the inverse sine, and there it is. It's that negative 18 degrees, which is very nice. So this equation then reduces to x equal negative 18 degrees plus 360 degrees times n. And this second one will be 198 because we're subtracting a negative. So 198 degrees plus 360 degrees times n. And therefore, in the range from between 0 and 360, the 4 possible answers to this problem are 54, 126, 342, and then 198. So 54, 126, 342, and 198 degrees. Okay, so that's it's kind of a little bit of a harder problem. Anytime you have to start pulling out these quadratics, but fortunately it did something very nice, and that is appreciated. So this is probably the last problem I want to do in section 6.2. I'm hoping that I've covered all the techniques that pop up in the homework, but I would suggest that before you finish that homework, go ahead and watch the videos in 6.3, because then I know that we've covered everything. There's kind of some stuff that seems to overlap a little bit in there, but I will see you in the next section.